This presentation really focuses on the hardware side of RFSoC, or RF System on Chip. And a good place to start when looking at the hardware is to look at the digital converters. So I'll start by looking at the A to Ds available from two of the largest manufacturers, Texas Instruments and Analog Devices. So I'm going to plot these with sample rate versus resolution. Now I've chosen A to Ds starting at 200 megahertz with 16-bit resolution. And as you can see, as you go higher in the sample rates, when you get to 10 gigahertz, the resolution drops down to 12 bits, which is pretty much what you'd expect. Now I'd like to plot the ones from Analog Devices, and again, similarly, at 160 megahertz, I can get 16-bit resolution. As I go all the way out to 10 gigahertz, I'm down to 12 bits. Now if I overlay these two, you really see that both manufacturers are following basically the same curve. But now what I'd like to do is I'd like to sort these based on the technology used for the digital interface side of these chips. So the first technology is parallel interfaces. In this case, or case of most of these converters, or all of them, LVDS. If I color code these, you can see which converters are using parallel interfaces. The next is a serial interface, and currently JESD204 is the most popular protocol for those interfaces. So let me plot those. And what you clearly see is as the sample rate goes up, JESD204 is the favorite interface. And we'll take a look at why that's true in just a minute. But the last converter I'd like to add to this plot is the RFSoC, which uses parallel interfaces, but the interfaces are all contained with the converters on the FPGA chip. So in 2017, Xilinx introduced their first RFSoC part with converter rates for the A to D at 4 gigasamples per second, or 4 gigahertz, and resolution of 12 bits. In this past year, in 2020, they introduced a new part designated, or new parts designated as Gen 3, and that brought the sample rate up to 5 gigahertz for the A to Ds with 14-bit resolution. I should also add that since RFSoC has been entered, or has entered into the marketplace, some of the other manufacturers have been starting to produce converters in the gigahertz range that do use parallel interfaces, and you'll see why in a minute. So I'd like to also add these. These are TI A to Ds that are running up to 6.4 gigahertz with parallel interfaces. So everything I've shown so far are A to D converters, but the exact same technology applies to D to A's. So this is basically the same for whether you're looking at A to D's or D to A's. So let's take a look at these interfaces. In a typical data acquisition and FPGA processing system, you see an A to D or a D to A converter. I'm going to focus on A to D's just for now. Interface to the FPGA, and then in many systems there's another interface to bring data on and off this card, let's say to storage somewhere else or for additional processing. What I want to concentrate on is the interface between the data converter and the FPGA processor. So if we look at parallel first, for a 14-bit A to D as an example, I'll have 14 pairs of parallel signals running between the converter and the FPGA, one for each bit. Typically that'll be accompanied by another pair for clock. And it's pretty simple. Each sample put out of the A to D is sent over the parallel interface accompanied by a clock. If we look at the serial interface, we see less signals, but these are gigabit serial lines running much higher rates, so you can move more data over less lines. Now looking at the RFSoC solution, we're talking about the A to D and the FPGA all in one, all on the same IC, so there is no internal signals or signal routing. Everything is self-contained. And now's probably a good time to look at some of the details of the RFSoC. So what is an RFSoC? Well, the FPGA part of the RFSoC is based on UltraScale Plus Fabric. In it, you'll find resources you'd usually expect in an FPGA: programmable logic, DSPs, memory, there's high-speed interfaces. The system on chip component is a processor system or subsystem containing 6 ARM processors and a range of peripherals including USB, SATA, PCIe, 1 GigE, all giving you access to those ARM processors. The RF part of the RFSoC are the data converters. So there are 8 A to Ds running at 4 gigahertz at 12 bits, and 8 D to A's running at 6.4 gigahertz with 14-bit resolution. But as I mentioned earlier, Xilinx introduced their Gen 3 parts last year, and that upgrades the A to Ds to 5 gigahertz with 14 bits, and the D to A's are now up to 10 gigahertz. So let's compare the different technologies and look at how each might affect your choice of converters when you consider PCB design, data path latency, physical size, power consumption, and cost. Let's start with the PCB design. A typical PCB layout for a parallel data converter looks something like this. we see the A to D in the center, and for each bit we see a signal pair and one additional clock, as I said, for one additional pair for clock going to the FPGA. The reason why some of these pairs are squiggly is because all the signals need to arrive at the FPGA at the same time, which means all the routed signals need to be the same length. The squiggly patterns, sometimes called tromboning or trombone tuning, is used to add length to the signal paths that are shorter distances between the converter and the FPGA. This allows you to match all the signal lengths. This type of interface is limited to converters running at about 1 gigahertz, and I'll talk about that in a second. Okay, the PCB for a serially connected A to D looks something like this, with the A to D in the center, and in this case only 4 pairs of signals. But these are gigabit signal lanes, and they're running at much higher speed, so they're moving as much data but with less pairs of wires. These can support converters up to the 10 gigahertz I mentioned earlier on the chart. Now, the last is the RFSoC, where the A to D, and in this case the D to A's, are all contained on the FPGA, so there really is no PCB routing needed. Now I want to go back to the parallel interface for 1 second. I said here that parallel interfaces can handle A to D's up to about 1 gigahertz. But I did mention earlier that there are A to D's out there that go up to 6.4 gigahertz using parallel interfaces. Now if the parallel interface tops out at around 1 gigahertz, the only way to handle the higher rates is to transfer the data over multiple interfaces. So the 6.4 gigahertz A to D actually has, I'm showing 3 here, but it actually has 4 sets of interfaces to handle the data bandwidth, which becomes a PCB routing challenge because you have so many lines now that need to be on there and matched, and does really become a challenge in applications with tighter space constraints. So now let's look at latency. In this case, I'm defining latency as the amount of time needed for the signal, the analog signal, to enter the A to D and propagate through all the circuitry and eventually end up where the digital representation is needed, like in the FPGA. So graphically, it's from here to here. So let's take a look at the latency for each interface. Parallel provides the least latency, anywhere from 50 to 90 clock cycles for the analog signal entering the A to D to appear in the FPGA where it can be processed. I did this in clock cycles. You could do it in nanoseconds too, but because different A to Ds are running at different speeds, it's a little bit easier to compare if you just bring everything down to clock cycles. The RFSoC is pretty close. It's around 86 to 166 clock cycles. The serial interface, though, has the longest latency, many times more than the parallel or the RFSoC. And this is because the process of serializing that data using the JESD 204 protocol, then receiving it at the other end and deserializing it and then lining it all up takes a fair amount of processing. So if low latency is a requirement for your application, serial really isn't the solution. And what are applications that care or don't care about latency? Well, one that doesn't care much about latency is data recording, where you might have an antenna receiving a signal, then converting the signal in the A to D, possibly encoding some more information about that signal in the FPGA, and then passing it on further down the system into a recorder or a computer recording the data or some other storage device. In this application, the data being stored is being stored for retrieval at a later time. So if it takes a second or 10 seconds or a minute to get that data from the beginning to all the way at the end, which is the recording media, it doesn't really matter. As long as you don't lose any data, you're good. So in this case, any of the technologies will work. An application that is affected by latency is electronic countermeasures, where you may have an airborne system that receives a radar signal from a tracking or targeting system on the ground. Now in this case, the FPGA needs to process that signal to modify it to look like a return signal from a plane that's maybe further away or traveling at a different velocity. Basically, something to make sure the ground targeting system can't get a fix on your position. Then it needs to transmit that signal back to appear to be the bounce of the original radar signal. And this has to be done quickly and with a determined latency. So in this application, JESD 204 is a problem, and the only solutions really are parallel or RFSoC solutions. Okay, so let's compare the amount of physical space needed for each solution. FPGAs are available in different gate densities, and the FPGA fabric in the RFSoC contains about 1 million gates, which would be considered a high-performance FPGA. So I found another FPGA with a similar gate density, and I'm using that here to represent the FPGA in these other solutions. Now all the components I've drawn are to scale, so you can actually compare what you're seeing on the slide in terms of how much space each solution needs. So RFSoC has 8 A to Ds running at 5 gigahertz, but they're all within the part, so they're in the same footprint. Now I found 3.2 gigasample per second serially interfaced A to Ds. These are actually dual channel parts. So to get 8 channels, you only need 4 physical bodies on there. And similarly, the parallel A to Ds are also dual channel, so you only need 4. But if you look at the size, you see that they're much larger than the serial A to Ds. And this is because to move the samples, the 3.2 gigahertz samples, it requires multiple parallel interfaces, as I showed earlier. So those multiple parallel interfaces mean more pins on the A to D, which requires a bigger physical part to provide space for all those pins. So if I go back to the RFSoC, I have 8 10 gigahertz D to A's, but again, they're on chip, so it's the same footprint. For the serial system, I have, again, dual 3.2 gigahertz D to A's, so I add 4 more bodies there. And for parallel, I also have dual 3.2 gigahertz D to A's, so I can add 4 bodies there. But there is a problem here, and that's because the multiple parallel interfaces, each for the A to Ds and the D to A's, require over 56 pairs per chip. And if you look at that as individual signals, it's 112 signals or 112 pins. Now, FPGAs in the 1 million gate range usually have about 600 parallel I/O interfaces. So the only way to connect these A to Ds is to reduce the amount of channels. So what I end up with is to basically connect up to 600 pins, I end up with a 4-channel A to D and a 4-channel D to A system. The RFSoC includes 6 ARM cores, and for the serial system, I found a standalone ARM processor with 6 cores, actually the same cores that are used in the RFSoC, and it's about this size. I also use that ARM processor for the parallel system to include that component. So in terms of area in millimeters squared, the RFSoC takes up about 1,600 millimeters square. The serial interface system takes about 2,860 millimeters square, and the parallel interface system is about 3,210 millimeters squared. But again, this is a 4-channel A to D and D to A system versus the other 2, which are 8 channels. As far as power, the RFSoC requires about 28 watts. JESD interface system requires about 52 watts, and the parallel interface system is about 34 watts, but again, it's half the amount of channels. In terms of cost, the price of the RFSoC can vary depending on temperature and speed grades, how you get it, but I chose a part that's about $8,000. For the JESD solution, the total cost of the components is about $13,200, and for the parallel solution, the total cost of the components is about $15,200. And again, that's for half the amount of channels. So in general, the parallel interface converters are more expensive than their JESD equivalents. Okay, so let's compare these 3 solutions side by side for an overall comparison. If I look at starting with the A to D speeds, as I said, the LVDS parts, you can get, the example I showed was 3.2 gigahertz, but you can actually, that's a dual channel part. So when you combine the 2 channels, you end up with a 6.4 gigahertz A to D, and that's what I showed early on in terms of what's available from the different vendors. Serially connected A to Ds, you can get up to 10 gigahertz, and the RFSoC solution with Gen 3, you can get to 5 gigahertz. On the D to A converter side, similarly, you're looking at 6.4 gigahertz max for parallel. For serial, you're looking at 9. I said 9 plus, but you can actually get to 10. And then also RFSoC in Gen 3 is 10. And in each one of these, I kind of color-coded them, with green being the best solution, yellow being kind of neutral, and when I show red, it can actually be a problem. As far as channel count goes, on the parallel A to Ds and D to A's, you're looking at 4 and 4, or if you're going to run them at double speed, you're going to lose half the channels, so you're down to 2 A to Ds and 2 D to A's. Serial JESD 204, you're going to be running 8 A to Ds, 8 D to A's, and RFSoC, again, you're at 8 and 8. PCB design, again, with the high-speed LVDS interfaces, you're running a lot of signals, and you're running them in matched pairs and in matched groups. So the PCB design, especially for a very small PCB, can be difficult. JESD, the PCB design, is pretty straightforward. You need less signals, and the length matching really isn't critical because that gets handled in the protocol. And RFSoC, of course, is the simplest because there is no PCB wiring between the A to Ds and D to As because they're on chip. I mentioned here interface IP design. With the LVDS, it's really straightforward. It's just a data coming in with every clock over those parallel lines, which is pretty simple. Same thing with the RFSoC. JESD 204 can be a little more complex. The JESD core does have some complexities to it, and it requires you to do some adjusting and some fine tuning. So there is some complexity on JESD. As far as minimum latency goes, the LVDS solution is the best. At 50 to 90 clock cycles, that's the shortest latency. But right behind that is the RFSoC. For a lot of applications, 86 or 100, up to 166 clock cycles is fine. If you need low latency, the JESD solution probably isn't going to work. 1600 clock cycles is probably on the low side. It can be a lot more depending on a number of factors, including what's happening in between with processing. Size, again, the RFSoC solution is the smallest, the JESD is the next smallest, and the parallel LVDS interface solution is the largest. And again, that size I showed you, a 2110 millimeters square, is only for the 4-channel by 4-channel solution. As far as power, again, the RFSoC requires the least power. The JESD really on a per channel basis is the next one up, and then parallel, again, it's only 34 watts, but that's 4 channels, so double that. If you could get that on a chip, it would be double that, or 68 watts. As far as cost goes, RFSoC is the lowest cost solution. Now what I did here to kind of make these easier to compare is I took the price of the solution and I just divided it by the number of channels. So we end up with $500 per channel for RFSoC. We end up with $825 per channel for the JESD. And again, because I had to have the number of channels on LVDS, I end up at $1,900 per channel for the LVDS solution. So the idea behind this is to give you an idea. Depending on your requirements, different parameters might be important, other ones might not be important. What you notice, though, is that RFSoC seems to check off a lot of the boxes, or is green and yellow throughout, because it is a very good general solution. And if you do think that RFSoC is a solution that will solve your application, then I'll show you some of the ways you can get there with the quickest path possible. So RFSoC solutions are available from Pentec in our Quartz family. And regardless of what hardware you're using, the path is usually similar. You're going from the technology, the RFSoC in this case. There'll be circuit design, there'll be PCB design, eventually there'll be IP design and software design. At some point that'll go to manufacturing, and ultimately it'll get deployed. So the question really is, what's the fastest path to go from the technology, RFSoC technology, right to deployment? And to answer that, Pentec has our Quartz family of products. Now these are based on a small system on module, the Quartz XM. And to give you some idea of its size, it's 4 inches by 2.5 inches, and I'm comparing it to just a standard playing card to give you some perspective. Now the whole idea behind the Quartz XM is that it contains all the circuitry needed to operate the RFSoC. All the critical circuit design, the PCB design is in this SOM, or system on module, and it's delivered in a proven platform. And it's designed to operate on carriers, but there's a wide range of different carriers available, including custom carriers that you can design on your own. So to look at some of the components inside the Quartz XM, first of all, in the middle, shown in red, is the actual RFSoC chip. Then in addition to that, on the SOM, there's power management. There's 13 different power supplies, but the SOM itself only requires 12 volts. There's clock management and distribution. There's DDR SDRAM, 8 gigs for both the fabric, for the programmable logic, and for the processing system. There's configuration flash. There's health monitoring for voltages and temperatures. And the idea here is that all the connections are brought to the connectors on this board to the carrier, because when designing this board, we didn't want to make any assumptions about how customers might need to use it, so we bring all the connections out. All of the A to D and D to A connections are brought out differentially through these connectors shown in yellow. There's another connector to bring out all the clocking signals, and then pretty much all the other signals are provided through this connector in blue, and that includes all the high-speed serial interfaces and power. So really, the Quartz XM is the foundation of this whole family. We offer it in Gen 1 and now in Gen 3 parts, And we have all different carriers available. Starting with our 3U VPX carrier. We have a 3U VPX carrier that is now SOSA aligned. We also have a PCIe version of the board. We have a small rugged box that's also available. And we have a small form factor subsystem that's available for integration into bigger systems. So let's take a look at the 3U VPX first. So if we flip the board around and remove the cover, we can clearly see the Quartz XM. I've highlighted the SOM in red and also in the block diagram. And we looked at the SOM in a previous slide, so I'd like to highlight in blue the carrier and look at what's on the carrier. It has on it a timing bus generator, and that's responsible for generating all the boards that needed clock signals locally. It also accepts a clock signal from the front panel from an outside source, as well as accepting a system reference clock that can be used to synchronize the clock generators on multiple boards together. There are transformers that bring the differential analog inputs and outputs from the RFSoC to front panel coax connectors, and you can see those in the photo on the front panel. There's an SD card which has the Linux operating system on it and also has space for user data. There are also 8 25 gigabit optical transceivers, and these are connected to the RFSoC's gigabit serial interfaces, and we support those with the installed dual 100 gig UDP interfaces that are part of the factory installed IP. Also shown is the rear transition module, or RTM, which is a common component in VPX systems. The RTM provides access to the processor peripherals, as well as some general purpose I/O, and access to our multi-board sync bus, which is for synchronizing A to Ds and D to As across multiple boards. So again, if the goal is to take the shortest path from design to development, we offer development platforms. This is a desktop chassis. This is the front, this is the back. The RFSoC board plugs in here, the rear transition module in the back, and if the optical is an option on your board, then these connections on the back of the chassis bring optical out to standard MPO connectors. And what the environment looks like is a PC with Xilinx's Vivado tools installed, the Navigator Design Suite from Pentec, which is the host application development package. It's a BSP for the board, as well as the FPGA IP libraries. There are multiple interfaces that can be used between the development PC and the RFSoC board, but the simplest is Ethernet. When the RFSoC board powers up, it boots Linux, and you have access to the board's resources through a terminal session. So that's a quick look at the 3U VPX environment, but our Quartz family is available in a range of different solutions, from commercial to rugged and conduction cooled, like the SOSA aligned board. The block diagram looks a lot like the 3U VPX board I just showed, but SOSA is a specification being developed for rugged deployment in harsh environments, so the board is conduction cooled, and that requirement doesn't allow front panel RF connectors. So these need to move to the VPX backplane to this VITA 67.3C connector. And what it looks like is a block that houses 20 RF connections. Its mate looks like this, and it provides a blind mate connection for the RF signals. There's also room in the middle for an optical interface, so that provides 8 lanes of full duplex optical interfaces, the gigabit serial connections, the 100 gig I showed earlier. The SOSA spec also requires 10 gig, 40 gig, IPMC shelf management, so that's included on the board, as well as the 100 gig UDP interface I mentioned earlier, and connections for our sync board for multi-board synchronization. So for applications that are running in less harsh environments like desktop PCs or server PCs, we have a PCIe board, and it looks a lot like a high-end video card with integrated fans. The block diagram is essentially the same, but with changes where all the interfaces are located, and in this case on the dual wide front panel. And again, to provide the shortest development path, we offer pre-configured systems where the RFSoC board are pre-installed, software and drivers are loaded, and everything is tested. So this can be removed from the shipping box and development can be started immediately. Sometimes a board level solution isn't really a good fit for your application. So we also have a standalone small form factor rugged box. It's about 5.5 by 9 by 3.5 inches, and it's designed for harsh environments. So it uses military style sealed circular connectors. It's ruggedized, conduction cooled, and designed to IP67 for dust and moisture protection. And the RFSoC is an ideal match for standalone deployment because with the ARM processors running Linux and providing all the status and control functions, this can be done through our software API, and the dual 100 gig interface provides a high-speed data path for moving data in and out of the box with total data transfers greater than 24 gigabytes per second. And here again, when you look at the block diagram, it's essentially the same as the ones I've shown before, but the I/O connections are appropriate for the deployed space. The last model on this slide is a small form factor subsystem. There are certain instances where a board level product isn't appropriate and the rugged box is actually more than is needed. So this is a self-contained module designed to be integrated into larger systems. And just like our other system on module and carrier board sets, this is the same thing. In this case, this is the carrier with all the analog and digital interfaces to the outside world, and the Quartz XM plugs into this and provides a complete acquisition and a processing system all in this small package. The block diagram here looks again very similar, but with the I/O connections appropriate for the installation environment. So even with the options I've shown, there might be times where a custom carrier solution is needed, either because of a physical requirement or maybe because of a specific application requirement that needs a custom RF front end, and it might be best to implement that circuit right on the carrier. As an example, so for these requirements, we have a carrier design package. And this is all of the documentation needed to create a custom carrier for the Quartz XM. And it includes all the pin definitions and electrical specifications of the Quartz XM, 3D model of the board, as well as 3D models of one of our carriers, thermal profiles of all of the components on the Quartz XM, as well as thermal modeling and measurements we've done. It also includes the design of the 3U VPX carrier as a reference. So we're giving you that entire design, including the schematics. And the idea behind that is very simple. That is a known working platform, and we encourage you to cut and paste as much as possible because, again, that's all tested circuitry. PCB stackup is included for our carrier, as well as all the PCB design rules that we've used. And there's a general collection of questions and answers that we've collected from customers who've already designed their own carriers. And these include guidelines on how to approach the operating system and bootstrap requirements. There's access to Pentec Engineering for guidance and design review. And again, because we are providing you with the entire carrier schematic, basically that design, it does require an NDA. And we say that all carrier design sales start with a board sale. And the reason for that is very simple. When you're designing your carrier, most customers that have been doing this at the same time are developing all their IP and their software on our 3U VPX product. So when the carrier design and the PCB is finished, they can move that Quartz XM module onto their carrier, and at that point they have all the software and the IP created, and it's a matter of just moving it over and testing it. Also, the VPX card can be a reference to go back and check performance or use it as a debugging environment. So that was my last slide. Again, this presentation was more about the RFSoC hardware. If you want more information, please visit us at www.pentec.com. Just click on the Quartz icon right on the front and you'll go right to all the Quartz information. But I'd also like to say watch for our next seminar in the series, which is all about the software and the IP environment, and we'll be releasing that soon.